Swayam Prabha. Digital India. Educated India.
So now the next section we will talk about, and I'll try to speed up a bit and maybe skip a few things because I want to cover a few things at least. So we will now talk about something called natural loops. And we will only restrict our definitions, only our discussion to only reducible flow graphs. We will not worry about irreducible flow graphs because as we saw that they are sort of rare, they don't come so much in practice, and we have some very interesting properties of these nice reducible flow graphs, and we can come up with nicer algorithms if we use the specialized class of graphs. Now, So now, next we define what is called a natural loop, right? So if you have a package n to d, then a natural loop consists of all nodes that can reach n without ever visiting d, right? So this is sort of, you can take it as a definition, right? So if you have a graph where you can visit the node n, right, which is so you essentially, the picture looks like this. So you have a edge which goes to, this is your n and this is d. So all the nodes where you can reach n without even going to d are called the package, the natural loop for the package n to d, right? Like for example, if you have nodes here, there to come here, you'll have to pass through d, right? There is no other way. But intuitively, you can see if there are nodes lying between n and d, which are covered by this package, then those nodes will not have to touch d. They can directly come to n. And of course, there is an interesting property that d will dominate all nodes in the natural loop. So because you will surely be entering through d, so this will dominate all the nodes that you have in the set of natural loop. So what is natural loop? Natural loop is a set of nodes. Nodes are essentially basic blocks. Is a set of nodes in the control flow graph, or a set of basic blocks, such that you can visit the loop tail n without hitting the loop head, which is d. So here I'll say this is referred to as the loop head, and this is referred to as the loop tail, right? So now there is a very interesting property that if you have a reducible flow graph, then all loops can only be natural loops, and two natural loops can either be disjoint or can be nested, right? So it's possible that you have a natural loop which goes like this, you have a natural loop which goes like this, and they're completely disjoint, right? They do not talk to each other. Or it could be that one is contained within the other, right? So it means, so this is a set of nodes. So either, like if you have two natural loops and you have sets S1 and S2 corresponding to them, so either it is going to be the case that S1 intersection S2 is going to be an empty set, or it is going to be the case that S1 or S2, the other way around, is a subset of that. Got it? So they cannot partially intersect. So now every natural loop has exactly one package. That is how we had defined it. We said that, okay, given a package n to d, this is how we figure out the natural loop of that. And because if for every package we associate a natural loop, so we can use this package as an identifier for this natural loop. So I can just say that I have a loop for package 1, package 2, package 3. So in some sense, the package becomes an identifier for a natural loop. So in this case, can you identify the natural loops? Like there are two natural loops. One natural loop is corresponding to the package 5 to 2. The natural loop is, so if you think which are the nodes which can, without hitting 2, they can reach 5. Like 2 trivially, yes, but if you just accelerate 2 and you want to reach 5, you can. 3 is of course the case, 4 is of course the case, and 5 is the Similarly, if you have a natural loop goes from 6 to 2, In that case, we have the nodes 2, 3, 4, and 5 and 6. And you can see that this is a subset of this, right? So essentially there is these loops are nested. That is what it means. Any questions with this?
So that means that if we have a back edge, we'll always have a natural loop, right?
Yes, yes, yes. You have a back edge, you will have a natural loop.
Okay, thank you.
And the discussion in this section is only for reducible graphs. I'm not even talking about irreducible flow graphs. So their loops may not be natural. I mean, so that is why it's called natural loop. So there is a nice notion of what is in a loop, what is not in a loop. So I will skip this algorithm of finding a natural loop because it's not so difficult, but I'll sort of give it as a homework. It is there in the slides anyway, but I'll just keep it on the screen for some time if you want to look at it. But the idea is very simple. The idea is that you start with your this node and you keep on going till you get a node which dominates everything, like you get that loop header. So I'll sort of not talk about it. Let me. Okay, so okay, so now so there is this other very interesting concept of something referred to as the depth of a flow graph, and I think you will also hit upon this again when Ketkar sir talks about analyzing doing a data flow analysis, and maybe the subsequent lectures. I mean, Jyoti, or so all these lectures. I think you will probably come back to this notion of a depth of a flow graph. So what is the depth of a flow graph? So the maximum number of retreating edges in a cycle-free path is referred to as a depth of a flow graph. So if you take a graph and try to find out what is the maximum number of cycle-free paths you can get, the number of retreating edges on that is going to be the depth, right? So essentially what you do is you follow a sequence of edges, attempting to visit as many retreating edges as possible till you are forced to revisit a node, right? So for example, here if I start, I can pick this node, I can pick the first retreating edge, I can pick the first edge, I pick the second edge, I pick the third edge, and now I am forced to revisit this. So I have been able to cover only one retreating edge. Okay, let us try some other path. Let us try this path where I pick this edge first. Let's do it with a different color. So let us pick this edge first. Let's pick this edge next. Then I don't even have a retreating edge, so I did not get anything useful. So let us try more. So pick this edge, then pick this edge, then pick this edge, then pick this edge. Now you got a cycle. So now you cannot do anything more. So you still got a one retreating edge. So looks like this particular graph has a depth of 1. Got it? So you have to find out which path has the maximum number of retreating edges. So I did not try everything, but as much as I tried, it looks to be 1. So I should have exhaustively tried all possible paths. And whichever path has a maximum number of retreating edges, that is the depth of the program. Any questions? Okay, sounds good. So, so why is this an interesting concept? Because in some sense, it sort of captures the difficulty of information flow. It says that how difficult it is to flow information, because retreating edges are always a problem in flowing information, because you are trying to flow information in the forward direction. You are trying to flow information from the like in this direction, but then the retreating edges force you to start flowing information in the backward direction. But because you have flowed the information in the backward direction, whatever information you had flowed, that has changed. Again, it's required to flow that information. And again, then you, because of this backage, you will need to flow it backwards. And that creates a problem in like computing solutions over the flow graph. And you will appreciate it more when you do data flow analysis. So in some sense, it says more the depth of the flow graph, the harder it is to flow information through the flow graph. That is sort of the, I mean, it's not the right definition or anything, but it's sort of the right intuition if you think about it. So it's sort of like the way to sort of think about it. Like, why should I be interested in the depth? And you will see that if flow graphs have a lower depth, the algorithms tend to be efficient. If it starts having higher depth, the algorithms become more expensive. They take more time. So there is a very classic paper by Fong and Ullman on finding the depth of a flow graph. I should have given the year, I forgot. I think it's a pretty old paper. It's somewhere in the 70s. I think 70s, somewhere 76 or so, I guess. And they actually say that it is an NP complete problem, so it's not an easy problem. So given an arbitrary flow graph, finding the depth of an arbitrary flow graph is an NP complete problem. But if the flow graph is reducible, then you have polynomial time algorithms. So it is still very expensive. It's order n cube, and even for control flow graph which has parts, it's sort of n square. But still, that is expensive. But still, it's polynomial time. So we still have a polynomial time algorithm for computing flow graph. So that is something you'll notice actually when I start talking about compilers or these areas. I mean, we say even n square is very expensive. Like algorithms, will be very happy to come up with an n cube algorithm or an n square algorithm. We'll say, oh wow, I mean, I've solved the problem. But when you start talking about compilers, even an n cube is out of the question completely. Don't even think about doing something n cube. Even n square is expensive. Even n square, I think you should sort of maybe give up, because programs are very large, and like n square on a program becomes very, very expensive. So this ends my control flow analysis part. Any questions? I can spend a couple of minutes answering that.
Yeah, so for the depth of a flow graph, I understand that, yeah, it captures the difficulty of flow of information through a graph, but it's not exactly clear what this implies.
It's not clear what it implies exactly. So that is the point. So that's why I'm trying to give you an information. So it's a definition is crisp. This essentially says the number of retreating edges on a cyclic path. The definition is crisp, but then what it implies is this intuition that it sort of becomes a problem. Like if the depth is high, it becomes problematic flowing information because there is a backflow also. So there are more retreating edges, there is more backflow. That is the intuition. You will see it in the proofs. Like when you do proofs of data flow analysis, then you will see it in the proofs that it comes out. That you will see that when you do the best case analysis or the worst case analysis of data flow analysis, you will see that it will be parametric on the depth of a flow graph. That is all I'll say at the moment. Maybe you'll get more intuition from that. Yes.
Yeah. Again, I'm just shooting in the dark, but the back edge means a loop or something like that, right?
Yes.
You just unroll the loop and then there's no more back edge.
How many times?
I mean,
for example, you have a program which is while one I++. How many times should I unroll it to get the behavior of this program?
just completely unroll it.
How many times?
Completely, like for all iterations. If the number of iterations is
so
no.
I'm asking you, so how many times should I unroll? What is the right number to unroll it? So this is while true.
Okay.
So how many times should I unroll it?
Yeah, you can't really unroll it.
I can unroll it, but infinite number of times, which does not make sense.
Yeah.
So you cannot unroll programs and get the complete behavior.
Okay.
Right. So yeah, people do unrolls, and then you understand that you are losing things when you unroll it. So you can say, let me unroll it 5 times and try to understand what it is. Let us unroll it 10 times and try to understand what it is. But understand that does not tell you the whole, doesn't give you the whole picture. It still gives you a much lesser picture than, like, it tells you like much lesser than what the program is actually doing.
Yeah.
You can make guesses based on that, but that is the best you can do.
Yes.
Right? So, like, for example, even if I was doing some sort of okay, leave it. Let's not get into it. So that is what it is. In fact, there are even verification techniques which use this idea of unrolling a finite number of times. But then they can only guarantee things up to that bound. They cannot guarantee it. Yeah. So that's
Sure.
that's the.
Thank you. There's one more question. So
Yes.
When you say a flow graph, immediately these flow algorithms come to mind: mincut, max flow, all that. So
yeah, sure.
Is that useful in this context?
So of course, every graph algorithm that you have read is useful. Like, for example, there is a notion of cuts, and that is used in like verification literature a lot. So there you can compute something called cut points, and then you can do a very nice analysis across cut points and put them together to make the analysis. So there are important, most of them are useful. I mean, almost like all of them are. In fact, lot of the very like the papers we read and the very well-known like computer researchers and compilers were graph theoretics. Like they were actually working on graphs. So yes, they are all useful. But here we were trying to talk about data structures, which will probably help you in the next few days. That's sort of